So, with a little bit of delay, we start with the mini course of Agustin Somacal from the Sorbonne University, and he will talk about reduced models and machine learning for forward modeling and inverse problems. If you would like to do some questions, you can interrupt the talk because it's a mini course, so it's a little bit more interactive than a normal talk. So, yes, Agustin, the stage is yours.
Well, thank you very much for allowing this talk. And I will speak, as he said, a bit about things that not things that I have been working, but the things that are part of my research nowadays. And it's some techniques to try to approach PDE, partial differential equations. And at the end, we will talk a bit about some machine learning techniques also to try to solve the situations in which these other techniques doesn't work as well. So first, a bit of a menu of what we are going to do today. So the first thing, we'll need some motivation about the things that we would like to explain, to talk about. And then we have different situations, because for me, my background is from physics, and then I enter like a bit of mathematical world. And for me, it's kind of a bit difficult sometimes to understand both situations. I was very used to go to the practice and try to go abstract from the practice, and sometimes I find in mathematics that maybe things are too abstract for me, and then they go to the practice maybe 2-3 classes afterwards. So in this, I will try to do a bridge. So my idea is to be in all these steps, and what happens maybe from the point of view of the theory and the things that we can say through the theory, and then go through the practical implementation. So I have some, we have some links, and we have the Jupyter notebooks that I would like to show you a bit, that then I will pass you the link so you can also explore them afterwards, maybe now if you have the computers. And also we'll talk a bit about machine learning, because this part will mainly focus on how to approximate PDEs with linear spaces. And yes, it sounds good, there are a lot of guarantees in certain cases, but obviously you cannot solve everything. And so which are the hopes that some machine learning techniques can help, and one in particular that I'm working on, and it's for me it seems interesting, or at least to talk about it and to have an idea of how it works. So, and of course, yes, what was your name? Alexander. As he said, if you have any questions at some point, just make them, because it will be more interactive. I'm not speaking like 4 hours here constantly. So, motivation. We will focus particularly in the case of partial differential equations, and how, you can find them modeling nature and in many places in the world. So you probably know everywhere, but you can have how rivers flow, how you can build, for example, in a factory you have maybe pipes, and you want to know how the flux will move inside. Also, for example, planes, you have the wing of a plane, and you would like to understand, for example, optimize its shape. And so for that you have no problem. You have partial differential equation that will model all these systems and will allow you to describe how they behave in different situations. There are many advantages of this. One of them, for example, is that instead of doing this, one way you can do is just to build a thing and try to test it, and test it many ways, and at some point it will break, and you say, okay, you should not do this, do that, but that's super expensive. It will be nice if you can make all beforehand, find a reasonable shape, and make the final test with materials at the end, so that it will help you save a lot of resources to the optimization process. But exactly what we will need in these cases, for example, is to do an optimization. Even though we have we know the equations and we know how to solve them, maybe it will require still maybe a lot of computation power in order to do a full optimization and find the shape of in this case, the wing. And so we need to find a way of doing these things in a faster way than just doing a full computational solving. And so that's what we would like to do, present some techniques to do this in a faster way. So, which is the framework in which we are going to work on. So the idea is that we will work on, particularly in parametric PDEs. So we have like a partial differential equation, and this partial differential equation will have, when we write them, different parameters. For example, here the diffusion coefficient, and it can be the velocity in the wave velocity, I don't know, or the Reynolds number in the case of Stokes. Or in different situations, we will have parameters that once fixed, it gives us the solution, the complete solution of this equation. And so these parameters can account for many things. So one thing, as we said, like can be velocity, conductivity, many properties of the system, inside the system, but also it can be, for example, the boundary, like how is the shape of your boundary, it can change. So for example, in the optimization of the wing, the shape of the wing, yes, the airplane wing, there maybe the parameter is exactly how you parameterize this shape and how you will change it and how it will change the solution of the flow going around it. And so as we write it, it's like we have the space of parameters, we call it Y, and this will be mapped to U, which is the complete solution. So this is a function on the space, in particular if it's 2D or 3D or whatever is the solution of your problem in particular. So one of the things we will do is we call this forward modeling, is exactly trying to approximate this solution U given the parameter Y. So you give me a parameter Y, for example, a boundary condition, a coefficient, diffusion coefficient, and I have to give you the solution in your domain. And we would like to do it faster than usual solvers. And this, it's, as we have said, wing shape optimization, for example, and also climate prediction. For example, if you want to make many scenarios for the following 3 days, for example, to know if it will rain or not. Normally, there are like many simulations that are run, and this costs a lot. You need a lot of computing power. Maybe you would like to have more simulations to have a better prediction scenarios, and you would like to do them in a faster way. So this is the motivation for the forward modeling, that is going from the parameter space to the solution space of your PDE. Next, another kind of problem that also are interesting are inverse problems. Yesterday, Silvia spoke a bit about it. In this case, I will focus particularly on inverse problems related to partial differential equations. In this case, what we will have is, okay, now we think, we model the system. Now it's the opposite. It's not trying to produce a simulation. Now it's there is some system that I'm studying, and I will get from this system some measurements. So these measurements, typically, at least here, will be linear measurements. So can be pointwise measurements, can be maybe an average or things like linear. And I would like to, using these measurements, to come back to the solution of the PDE. So to reconstruct the complete, the complete function of the solution. And also, I could be interested also on doing the inverse problem and get the parameter of the that I may be interested in. So that the two problems are, one is called parameter estimation, when we want to go from here to here, and state estimation when you want to estimate the state. Okay, yes, the thing I wanted to say is these kind of things can be useful in many places. For example, in a factory you have a water plant or whatever, like also potato plant. This is because I had a teacher in the university that told us that at some point he had to work in a factory in which they had like a potato, smashed potato that had to go, and you can describe it like as a fluid, and they had problems and everything, and they had problems if there was not too much, it was too not too viscous, so it gets trapped at some points, and you have to clean everything, and so it was important to know at every point if everything was flowing well or not. Just to give you an idea of the thing that you have, the factor you cannot measure everywhere and know what's happening everywhere. And maybe if you have some measurement at some point, some sensor that you will put, you would like to have an idea what is happening inside without having to do an X-ray to all the factory or something like that. Okay. So that's basically the idea. So you can, if you have information, some point-wise information, you will use to recover everything, and then you can maybe take decisions. Okay, I have to stop the factory because I have to clean everything, or I can continue and everything's okay, or everything will blow up because okay, things are not going well with pressure inside. And also because this can have a lot of effects, and you need a quick answer. You need also to have to be able to do this mapping in a faster way, not just wait 2 hours until the simulation ends and find the correct parameters. And also, this we will not talk too much, but just I mention it. Also, these measurements, they can be in a passive setting. It can be given, like someone put the sensor somewhere and you cannot move them, and so okay, you have to do what you can with what you have. Other situation is active setting, in which you will decide where to put your sensors and maybe use this to optimize or get better results at the end. Okay, well, just to recall, we have forward modeling going one way and inverse problem going the other way. So, okay, we can go to the Jupyter notebook. This is working well because I want to show you the examples here. Okay, perfect. Okay, this Jupyter notebook, well, that was where the link, and afterwards I can give you the link also. You can enter and download and play with it. It's a bit to gain intuition on what we are going to go through this first. And so in particular, we will be working with one particular PDE, which is the diffusion equation. And the particular thing is that we will have this coefficient that will be our parameter. And in our case, we will have, let me just run the things. Should we run that? Okay. The thing is that we will have 4 domains, okay, and each one of these 4 domains will have possibly a different diffusion coefficient. And the idea is, for example, if we want to do forward modeling, is like I give you the 4 coefficients that correspond to each one of these 4 areas, and I have to give you the snapshot, the complete solution of this equation. The other option is I will get some measurements here, and I would like to also build this approximation of this the solution. Okay, that's the 2 things we are trying to do.
Can you
Yes.
repeat the first one?
The first one is I will give for example here the 4 parameters are set all to 50, so the diffusion coefficient is 50 everywhere, and what I want is to give the approximation. So give the complete solution from the 4 parameters that I will give. So in the sense it goes like just solving the differential equation. So it's solving this PDE once I give you which are these.
So the forward problem.
Exactly, the forward problem. Yes,
Okay.
exactly. Yes. The thing is that, okay, you can solve it just putting the solar and solve the forward problem, or you can use an approximation method that should be quicker than put the full solar. Okay? And so just to give an intuition of this, so here there is no time, it's just the final stationary state of this equation, in which the heat or the diffusion is already arrived to the stationary point. And so it's just intuition of how this may work is that, well, here everything has the same diffusion coefficient, and in the border we have set the boundary condition equal to 0. So basically what it's doing is just going to 0 to the sides and has more concentration in the middle. But if we change, for example, the parameter here, and if we augment, we have more diffusion coefficient, intuitively what it means is that what the heat or whatever is there, it will diffuse faster, and in the other side will diffuse less. So there it should in principle go a bit down with respect to the others. So we do that, we see that here it went down a bit and moved a bit toward the others. We put the maximum, or we can see it a bit. If we do the opposite, it means you will retain as much as heat or whatever is diffusing inside, because it's not diffusing. The rest is diffusing a lot, but you are not diffusing. So if you go the other side, everything will concentrate there. Okay, if you go almost to 1, it will basically stay there, and the rest will just flow to the other side. Okay? Just to get a bit of the intuition of, what does it do this equation? And you can then you don't know, you can play a bit more to gain more intuition of these things. If you go down here, then concentrate it on the other side. If you do this, well, it will be both, because both have the same. Yes? Okay, it's faces. Okay, good. So this is the question we are going to be working on with to test numerically all the things that we are going to explain afterwards. Yes, okay. I think this is good for this part. So, okay. Okay. Perfect. So we are good until here. So just recap. The thing is, we are, for example, if we are doing the forward modeling, we are going to be given the y, and we want to get the approximation just in a faster way. If we are in the state estimation setting, we receive the measurements from a real state that we never have access to. And from these measurements, we would like to reconstruct something that, well, should be similar to the original state, but, well, they have some, it's an approximation, so will not necessarily be exactly, but, well, depending on the thing we want to do, will be good or not. So, second part, I don't know in time at this point.
It's going to do 11, but it's going to be way late.
No, I can continue a bit more if you want.
Yes.
Yeah, of course.
Okay.
About 14 minutes.
Okay. Well, so now we are going to enter. The idea is we want to use linear methods to do these two jobs, like inverse problem and forward modeling. And we are going to first explain a bit about the theory behind it, and then go to the practical side of it. That always has, you have to add more work to it. So, just to have a picture, we are going to work particularly with the parameter to solution manifold. What is it? When we have this partial differential equation, in our case was the diffusion equation, our parameters were the diffusion coefficients. So if we vary these diffusion coefficients, we get one particular parameter, we will get one complete solution. So this manifold, each point here, it lives like in a space of infinite dimensions, because it's the function that represents the solution of our differential equation. Okay? And so when we change our parameters, here for example, if everything is 50, if we change them, we move through the manifold, and we will get another point here that represents another solution of our differential equation. So we can continue moving around. And so the thing is that, okay, this manifold lives in the infinite dimensional space, but it's something that has shape in this infinite dimensional space. But the thing is that our solution, our differential equation, will live all here. And so the idea is that we will try to approximate this thing with a linear method. Well, maybe in the notebook I pass it a bit fast, because this is just a comment about, okay, in theory this is infinite dimensional, but obviously when you want to solve things and go to the computer, there is no infinite computer to do this kind of stuff. So you have to discretize to do something. So in practice, this space will be finite dimensional, but possibly a very big dimension. So for example, for our problem here, we have discretized all this domain, and the dimension is 225. Just to give an idea.
So are there any assumptions on V-line convexity or any separability, anything?
In principle, it's Banach phase, I would say, and the thing is that then afterwards, more about the manifold itself, depending on what or which is the problem and the guarantees you will want to have with your linear approximation spaces, then you will need some more assumptions, and then you will show, for example, if you may get a very good guarantees of approximation, but for certain type of equations that give these assumptions. Like for example, typically, then we will see that elliptic and parabolic differential equations may have very good approximation properties, but for hyperbolic, everything breaks. So, okay, just a bit explanation about how well this is solved in practice, and because then we will use it also to understand a bit some other things. Maybe you already know a bit about the weak formulation for sure, but just to recap, so we have our differential equation, and we'll try to write it in a weak formulation, which accounts to putting a test function and integrating this equation. And so in our case, this will, because this coefficient has in each domain, it's different, so we'll have like a sum for different domains. And so to recall that, okay, you have we can do, for example, finite element methods. In our case, it was more like polynomials that we use as basis to build this approximation. But in principle, it will be any method that you build a basis and you try to find, for example, in the finite element methods, for each point of your discretization, you will try to see the couplings between the two neighboring ones, because normally if you are far away, you will not intersect with the one you are looking, so your intersection will be 0. Maybe if you have polynomials, then you have to take more care, because then when you do the integral of the gradient of two polynomials, then you will have some thing to add into your matrix. But basically, this is to say that at the end, when we get the solution of our differential equation, it just accounts to solving a linear system, in which, because we wrote our solution as a sum of basis functions, we want to find which are these Ci, and it will account to solve this problem, in which we are going to give f, and this matrix A that takes just the gradients of your basis function that you can pre-calculate beforehand, because you know which are the basis functions for your discretization. And once you get to know which are the new parameters, you just have to plug in here and you will get the new A that you have to use to solve the system. But I think everything accounts to solve it a linear system. Just a comment, you can do this thing also in graphs. So instead of maybe having a 2D function, you will have functions that go through the edges, and you have to take into account that maybe in a point you have a function that will split in many, because your neighbors maybe have many points and some have less. But at the end, it accounts to do more or less the same stuff. Though, yes.
Can you explain a bit what are the phi j and phi? Because I don't see from the picture the function.
Okay, the phi are like the idea is that you will have, for example, maybe you can write. So imagine you have in 1D. Okay, so imagine you are in 1D, and the idea is you want to approximate something, of course. No? You will approximate it using the fact that it's a differential equation, and you want to solve it, you have some parameters. And the thing is that you will discretize your domain, because you cannot be continuous. So you will discretize your domain, and so you have some discretization here. And what you will do is to say, okay, I will create some basis functions that will be, for example, in this case, like triangles. So I have this triangle, I will have this triangle here. So at the end, your discretization is giving you how many elements in your basis. And so what you are interested at the end is, given your equation, because you will write u as sum of this I, for example, it will be g. For example, ci, you will like to find these things. And so the only thing at the end is you need to know is these calculations that you can do it beforehand, because the phi, phi g you have already chosen. In this case, okay, they are triangles, but it can be also like polynomials. Like it can be some kind of polynomial, for example, Lagrange polynomial, and that's what we use in truth. And so basically here, what you will do is to calculate, for example, the gradients. And so we will try to do the matrix gradient phi, gradient pg, which is the one there, and integrated over the space. Normally here, because they are triangles, will be integrated 0, and the only thing that you will care about is calculating here. And because the gradient is just a constant function, which happens with this intention of drawing, we will be just multiplying the 1 and 1, for example, in this case, because the slope is 1. Okay? So basically, it's once you choose your basis, you will have just to integrate the gradients with respect to each of the elements. And that will give you the matrix AEG. Okay, good. Okay, and this you can do it in 2D. Then the function will be like more like a cone, a pyramid or something like that. And well, in graphs in particular, the thing is that maybe now you will have many neighbors, but still will be in each edge will be one-dimensional. So why it's a bit different, particular. And the only thing in graphs is that maybe the boundary conditions is not so clear where they are. And sometimes you don't necessarily need them, so it's interesting. We'll not focus on this, and just to show, because I wanted to mention this, because we are working on this inverse problem in which we have measurements of pollution around Paris at some points, and we want to build like a map of pollution around Paris. So at some point we build some effective model of the pollution going around with the reaction diffusion equation, and we have to model this with using the streets of Paris, supposing like the pollution goes only through the streets, and so you can model it like a graph and say, okay, diffusion will go around there like in a graph. But the basic idea you will use at the end is more or less the same that we have been speaking about. Okay. In our case, as I said, our basic function is not these triangles, but Lagrange polynomials, and the discretization is not uniform, but we use the Chebyshev nodes because it has more best guarantees that the approximation will be better, and especially because we have the 4 domains, and when you are near the discontinuity on the coefficient, this may have problems. So you need to have more discretization, the distance smaller. Yeah. Okay, good. Okay, now we go to how we will approximate this with a linear space. Okay, so we had our manifold. We have our solutions. That this is a complete differential equation, a solution of a differential equation, and we'll try to approximate it with a linear space of dimension n. And so the question is, okay, this linear space, okay, is it good? Is it not good? How far it is to the rest of the points in the manifold? And this, okay, can be useful in many ways, because once we have this linear space, we can do, instead of working with the manifold, so instead of working with the full solver, the full problem, we'll work only with the elements of this basis, and we can do forward modeling and inverse problems anyway without problem. And the difference is that, well, we have spoken before, all this decomposition gives us a linear system to solve. And the thing is that now, when we have this space, instead of using this phi, phi g, will not be the finite element method discretization, not the Lagrange polynomials, but our basis that we build on this space. So the elements of this space will be our phi, phi g, and so this n that we'll be using will be much smaller, and so the linear system we have to solve is much more than the full dimensional space. And for doing inverse problem, we can also do the same, because the thing is that we have now some measurements of the real background problem that we are trying to study, and we can pre-compute on this in the same places how are the values that each of the bases of our Vn space what they measure, what they give us, and so we can use them to build also another linear system that also will be small, like this. Well, instead of n times n, will be m times n, because we have n measurements. Typically, n should be bigger than n, so the number of elements in your space. But then again, it's a reduced problem, in the sense that you don't need much information, and you are using only the basis you build, the function basis of your linear space. Okay, just to say that, yes, we are going from a big n to a smaller n, and we gain computation power there, basically. Okay, the question is, which is the best linear space that we can build? Because, okay, we can build just a linear space, just plugging some random things, but it may be very bad to approximate the kind of problems we want to approximate. And also, when we ask this question, it's also in which norm. Because, I mean, if we do it in the worst case scenario, we'll give something, but if you do it in a 2, maybe we need something else. So, depending on your problem, depending on what you're doing, you may find different spaces that are good in different scenarios. So, for that, from theory point of view, there is this concept is called model width, which has a lot of things, I think. But the thing is, basically, what we have is we have our linear space, and we want to measure the distance between our manifold to this space. And so we will choose. So U is the element in the manifold. V will be an element in the linear space, and we will want to infimize on all the V belonging to this Vn space, and try to make the worst case scenario in the manifold. So it's like a competition between the two things. In the manifold, you will try to, like, two players, one trying to make the big distance possible, and the other one trying to approach it the nearest. In particular, if this is a Hilbert space, this V will be just a projection of the U on the linear space. And so then, what is the Kolmogorov width? Because here it's like, okay, you give me a linear space, you have your manifold, and with one linear space, one manifold, you get a particular distance, the worst case scenario. But then you can also infimize over Vn. So now we have the right to move our Vn space and try to find which is the best Vn space that makes this distance the lowest possible. So now it is another player, which is how you move this Vn space. So basically, we move the Vn space. Now the worst case will be here, and then at some point, maybe if we find the correct one, we get a linear space which has distance to the manifold that is the shortest possible. Okay. And so that's the column width. And the thing is that this quantity, theoretical, because in principle we are not assured that we can get to arrive to this linear space in particular, but tell us, for example, for a given problem, if a linear method would be a good idea or not to use it to tackle this problem. So, for example, if you know that this column width decays with the dimension n, so in principle, if you augment the dimension n of your linear space, you should get better and better approximation of your space because you have more ways to basically fill this manifold. And so, if the problem you are trying to do behaves well in the sense that decays faster this column width, then it means your linear method will be good, or will be a good take to try to solve this kind of problem. But if you know that your column width is not good at all, that will decay very slowly, then you may have to go for another kind of methods to solve your problem, because your linear method will be doomed to not to work. Okay? So from a theoretical point of view, this quantity is the important quantity to take into account for linear spaces to know if you will use it or not. A linear space to approximate this manifold. Another related concept, it's the optimal spaces in a mean square sense, and it's instead of okay, in this case we are like trying to find the worst case scenario, so always this supremum here is trying to find the worst scenario, and here what we'll have is the error in L2, and so this is just trying to find the projection of U in V that minimizes the expected value of this the normal square. And so when we look at this, we see that okay, this can be diagonalized, the covariance operator of your space, and you can write it as so basically this is related to principal component analysis. The idea is that you will try to build your space choosing at each step the elements that takes the most of the variance possible at each step. So when you have n elements, basically your error that you are making here will be just the sum of all the eigenvalues that are left aside because you have not yet chosen them. And so this gives us another way of creating a linear space that can be also optimal in this sense. So the thing is that yes, okay, we have the theoretical guarantees that make to tell us the linear space will be good or not. And in practice, the thing is that this is we need to go and find an algorithm to effectively find this kind of linear spaces, because okay, we know that column width will decay very fast, but we don't have an algorithm to approach something similar to it or the same linear space. Then still we are not getting a good approximation. So it's not enough to have the theoretical guarantee, we need to have also a good algorithm to do that. And so this quantity, this is also again the distance between M and the manifold, will tell us somehow for a given algorithm which is the best thing it can do, and we will try to relate it always with the column width. So try to find a way to say, okay, you give me an algorithm, with this algorithm I find a linear space. Is this linear space also with increasing dimension decaying, so the error goes down as fast as goes down the column width, even though you will not reach the optimum, you still can get, in some cases, also good guarantees for different algorithms. And so this is a bit like I commented before. We know that for elliptic and parabolic PDEs, this column width decays like exponentially with the dimension n, well, n small should be here, and the dimension n of the linear space, which gives us,
Why is that the maximum?
in this case, I think this case, because we are in Hilbert space, I mean we have projection on the I mean, I think in this case, yeah, I'm not sure. But,
So it depends on the shape of n. Of the
yeah, I mean, yes. Okay, we can think it afterwards. I'm sure. I guess. Okay. Well, now linear space in practice. I don't know if you want to do a breakdown.
10 minutes.
No.
Ah,
Like
left.
10, 15 minutes. Ah, no, 15 minutes, yes, sorry. 15 minutes left.
15 minutes left.
Yeah.
Okay.
Quarter.
No problem. Okay, so now we have seen a bit of the theory behind, and now we want to go to the practice of how to build these linear spaces with different strategies. So, as we said, the optimum is not attainable because we cannot find the optimal linear space. Also, V, because I mean V in print also is finite. I mean we have a discretization. And even there, also we don't have access to the full manifold. Normally, also you will sample the manifold some way somehow. You cannot have the full picture. So even if you had a full picture, maybe you could like try to optimize that. Even there, you have to optimize something that is not will never finish in your life to do it. So you will have to do something to still get some good approximation properties. So one of the things is this: we will have to sample the manifold. So we have some precomputed. So we have like an offline stage which accounts to compute different solutions of the manifold. So we sample the manifold. We will have them stored somewhere. So this can be computationally extensive. So here you can use maybe your favorite solver that it takes a lot of time, or you can parallelize whatever. You get a lot of snapshots of solutions of these manifolds. So you have more or less kind of a picture, and you will try to use this as a way to approximate your linear space using this data. And so, well, what we expect, yes, is that this new approximation, this VN space that you will reach in reality, is it near or not to the optimal space? Okay, and then in the online stage, as we spoke before, once you have your linear space, you will just do to solve both problems. It's just solving the system, the linear system, with your linear space that you have just did, as we spoke before. So the idea is how to build these spaces. Okay, just this to recall that now the n that we will use here will be much smaller than the original one that was the space that you will use in the sum. So, just first idea, random sampling the manifold. So you random sample the manifold and you will build your linear space with the first n sample you get. So we sample once, you sample twice, and we just create our linear space out of it. Not much mystery about it. One comment is that here we will have that each element of our space belongs to the manifold, so is itself a solution, a particular solution of the differential equation. However, once you move inside, so when you want to project when solving one of the problems, you may lay outside, basically, right? Because you are just using this linear space. But the two elements you are choosing at the beginning are from the manifold. Okay. Then there is another algorithm that is called greedy algorithm. And so the idea is now, okay, we want to do maybe a bit better than just random. And so what we will do is, in an offline stage, we will sample many elements of the manifold. So now we gather a lot of information. And what we will try to do now is to follow like an iterative process in which at each step we will choose one element of all these sampled elements that it's the worst, the one that has the biggest error using the previous linear space that we have built before. So in a general case, it's imagine you have already built a linear space until of dimension k minus 1, and now we will build is try to find, we will compute for each of these elements here, we'll compute the distance, the error that they have to the linear space that we have before. And we will choose the one that maximizes it. So for example here, this was our first element, and our second element became this one, because it's the one that is farthest from the first linear space that we gave. Okay? So this is a greedy method because at each step we will get the worst, the one that has the worst error, but obviously it's not necessarily optimal, because maybe if you choose another path that not necessarily goes always from the maximum, you will get at the end a better linear space. And for the first element, we'll choose simply the one that maximizes the norm between all the elements, just to initialize it, and then you start this iterative process. So the interesting thing is that for this algorithm in particular, have improved that if the problem you are working on, is the problem you are working on has a Kolmorov width that decays, for example, exponentially, then this algorithm will give you an approximation that also decays with the same rate, even though it will not be as optimal as the best situation, but will decay with the same kind of width. So okay, it gives an interesting, I mean, it's a guarantee, it's the thing that we needed to know that this algorithm in particular, together with the particular problem that we are dealing with, will be the good combination to approximate the linear.
Sorry, but we are just doing this in order to do not evaluate a lot of times the element of the manifold, right? We would like to build this linear space because we don't want to compute a finite grid of the manifold M, right?
Exactly. I mean, if imagine, for example, the forward problem. Forward problem is I give you the parameter of the differential equation, you get the solution. So this you can do it with your solver, your finite element solver.
It's slow. You don't want to do it a lot of times, but here we are just saying I need n elements of the manifold, but I would like to evaluate a capital K that is greater than n. In the first row.
No, okay. This step here, I mean, we need to sample more than n times because we need to build this linear space.
Okay.
And so this is before using it. So here it's just building the linear space.
Okay.
Once we have built it, then we will use it to approximate do a formula.
But here, capital K is also smaller than capital N, which is much smaller.
I mean, it's different number if you want, because capital N tells you the dimension of each of these points, which is the dimension of, I mean, which is the dimension of the space V. So the dimension of the space V in the when you go to numerics, it will be big because it will be the finite element methods. It will be like very fine mesh, for example. And so this V will be dimension will be very big.
Okay.
And so each of these points lives in this very big space. And K, it means just that I will get many of these
K is the number of evaluation, while also little n is the dimension.
Little n is the dimension of your linear space.
Okay.
Okay.
So there is no relation between the number of elements that I'm just picking, so the number of K and n, that is the dimension of the space, right?
For example, just in 2 dimensions, for example. So imagine V is 2 dimensions. So dimension V is 2. Now you have the manifold. And you will sample this manifold. So we have 9. So here K will be 9 because we sampled 9 points. Okay, and then we approximate this with the linear space, and this dn n will be equal to 1.
Okay.
But it's true that the element here, I mean, the dn space is dimension 1, but the elements here, they are still written in the original base because you still have a solution of with a finite element.
Okay.
I mean, it will be a long method, but the thing is that will be only 1. And then when you do the forward modeling and all that, you will use these vectors, and you will only need, I mean, a few to approximate things instead of going through solving the full thing with probabilistic dimension 2.
And you require that there is one element of the space Vn that belongs also to
the manifold.
the manifold.
Well, that depends on the method. Here, for example, because how we are building this space with the greedy algorithm, it will be always be an element of the manifold because we have at the beginning we sample things from the manifold. So all these samples are from the manifold. And once we are building this, we are always picking things from this sample data. So all of them belong to the manifold. Okay.
Okay. So.
Okay.
I don't understand the algorithm.
The algorithm.
Because I would take the admin. I don't understand the Rmax. I don't know anything about this algorithm.
Okay. The idea, for example, let me see. The thing is, at the end, you will like to minimize your error. Okay, it's true that at the end you need some kind of minimization. You want to minimize at the end. So beforehand, you will try to gather the most you can. So at the beginning, you try to build a thing in order to put in the bag as much as you can. So at the end, you will be able to be kind of sure, let's say, that everything will more or less cover. So what does it mean? It means that at the beginning, for example, if I had taken the mean here, it means I will have searched the one that was, for example, near. So this will have tell us like a vector that goes like this. And if I stop there, I want to use this linear space to approximate the manifold. The things that are there will be very big error.
Okay.
You see?
With the max, you can maybe look at the shape of the.
With the max, the thing is, you are sure, for example, if you take the max, you are sure that the max you are taking it. And then everything around, well, depends a lot how your manifold is, but if it's reasonably not so strange, then things will not be so far. I mean, will be more near than if you have chosen something that was maybe not as good. You see the idea, more or less?
Yeah.
Okay. So basically, in the offline stage, you have to build the thing. So you will build it in the worst case scenario. So I say, okay, now let's take the things that have the most error. So I'm sure that I'm covering everything up. And then when I have to go and use it, okay, everything that comes, well, I'm more or less sure that I have put some patches everywhere and I can deal with what is coming. If I go always minimizing, I will just go maybe around here, I don't know, and we get linear spaces that go one way and doesn't capture what is happening in the other side of the map. Yes?
Yes.
Some other question?
It's possible to choose the first sampling U1 randomly.
Yes.
Why you choose the first one with the max of the norm?
Well, yes, in truth, you can. I mean, you could do that also randomly. This, if you want, this is because okay, I was saying always linear space, but it's a subspace, so the zero, it's inside. You can think this as minimizing this when you have nothing. So you started from in the origin, which is nothing.
Okay, now I see. But I think that, and correct me if I'm wrong, that the algorithm doesn't change so much if I put the first element randomly.
No, probably will not change much. Yeah. Then we will see, I mean, at least in the examples here, also choosing the random algorithm at the beginning doesn't change much.
Okay. Okay.
But then I mean, depends on the problem. It may give different things. Okay. Good.
So you said before that for some kind of PDEs, you have the Kolmogorov width goes to 0 exponentially, right?
Mm-hmm.
But do you have like a general theorem for general PDEs that tells you that at least it goes to 0, or it could happen something strange?
I'm not sure. I mean, in some cases even I think it may not exist as
Okay.
it can, in some cases cannot exist even. Yes, I don't know, it depends on,
Okay.
I mean, you have to probably classify different problems, and some problems you cannot. Yes. Okay. Mm-hmm.
It's possible to sampling the manifold such a way we optimize the forward and the inverse problem and not optimize the sampling itself. Because at the end of the day, we linearize to use it in the forward and inverse model, right?
Yes.
So, okay, it could be good to have a good approximation of M, but we are not interested in that at the end of the day, right? It's possible to optimize in that sense.
I mean, it's true that you want to do that, but I mean, for example, for the forward problem, you know that you will be given some parameter of the that will be associated with that one point in the manifold, and it can be anywhere in the manifold.
Okay.
So there it makes kind of sense to optimize with respect to the manifold, because then when you are going to go, you will be given something. That's good. In the inverse problem, it's true that it's not maybe exactly like that. Then they have two situations. One situation is your sampling already given. I mean, you know where are you going to be, have the measurements, or it's active, or you can choose where to measure.
Okay.
So if it is passive, it's true that maybe you can do that. So instead of maybe calculating these norms with respect to the projections on the manifold, maybe you can do it using the measurements. I mean, you can measure this U and see which is the worst in that sense. So you will be optimizing your linear space given the measurements with this algorithm or whichever algorithm. You can do that. In the active setting in which you can build this thing beforehand, maybe you use it the same way here, and then you choose where to measure given the linear space you have chosen. And you can do that, and it's related with what Andrea told yesterday about these optimal sampling strategies. There is, I think, one slide afterwards, just a comment about it. So yes, you can choose maybe how to sample once you have your linear space chosen. So yes, depending maybe in which setting, you may change what you put here and how you build it, and which is the best situation.
That's
Good.
Can we have a break?
Yes.
Okay, so it's not finished. He is going to finish later. Now we can have a little break, and then
we will see in
30 minutes.
Okay, just fast recap. We are trying to approximate this manifold linear space, and we have different algorithms to do it in practice, with some guarantees or not that they may be as optimal as the optimal one. And so we have just seen the greedy algorithm that okay, will take it will be try to be as good as possible in the worst case scenario, and also last algorithm it's principal component analysis. So we start again with the we sample our manifold. We have a lot of data, and we can think this as data, some big space, and we will want to choose like principal components, like principal vectors that will try to capture the most of the variance of our data. So that's basically the idea behind principal component analysis. So for example, we will try to find something that takes into consideration this the variance that you will have in the direction in which the variance is bigger, and if you want to add more components, you will start going for the next direction in which the variance is bigger, also kind of iteratively, but in this case what we are minimizing is more like the average error that we are committing. In the other case we are minimizing the worst case scenario. So depending on the problem, it can be also useful to do this. And the thing is here, although our data originally was in the manifold, once we get the principal components, our vectors will not be necessarily in the manifold, because they will be just a rotation of in some direction, and not necessarily will lay in the manifold. When we have been doing the greedy algorithm, we are always we have been choosing the elements that were in the manifold. Although then when we approximate, we will go whenever the linear space takes us, we will be probably outside the manifold. So let's see all these methods, how they work in practice. So we had our notebook with our solution, and so we need to define our offline stage. We need to compute our solutions. So here, for example, the number of solutions offline that we will take. And this, for example, is to test afterwards and see, okay, our methods, how well they are behaving or not. The number of elements in our basis, can be different numbers. And for the inverse problem, how many measurements in the domain we really want to have. And so we have, different steps. First is how to build these solutions. It means the first thing is how we will sample our manifold. And so here for the moment we use just random uniform over the parameters, which will induce some sampling over the manifold. But you can use like also grid or maybe some other consideration. Should probably execute these things. So here we compute the solutions. Here it's just a bit of an intuition what happened if we change the values that we saw before, what we get. And just showing here some particular solutions that we may encounter, and we will try to use to approximate, or we will want to approximate. Okay, generate the reduced basis. So here we have all these methods that we have been speaking about. So first, the random generator just pick at random as many elements as our basis needs. So well, this is Python. This is just simply calling the right function to just sample. And we choose through all the offline solutions that we gathered beforehand, and we get the number we need. Then we have these, because, for example, this I've not spoken about, but also we could, like, instead of choosing, when we build our original space, our original V space, is done with the finite element methods in the fine mesh, for example. But you could do that also in a coarse mesh. Instead of using very fine, you use a bigger, not so small mesh. And so you can get also an approximation and do the same techniques. But those ones are usually not so good. For the same amount of elements in the basis, you will not get as good solutions as we will get with the other methods. But it's also a possibility. It's also in the space that you can build and use it with the same procedure. Then the PCA, principal component analysis, is just a function coming from scikit-learn library that has a lot of machine learning tools inside. And so for this, it just reduces to first fit, which means take the offline solutions, find the right vectors that characterize the data, and just get from the components the number, the first components that account for the biggest explanation of variance on the other. And finally, our greedy method. So here I have a bit more lines of code, but as you can see, here we have the argmax taken over the error that we will get from all our solutions offline. So we have our solutions offline, we're calculating the norm, and we will get the ones that is biggest. So with this we initialize our basis, we have the first element. And then we go for all the rest of the elements. And what we will try to do is to find the element that maximizes also the error with respect to the elements that we had before. So here we have our approximation using the basis that we had before, and we will compare it with the true solution, and we will take the maximum. So here is here it's basically doing this part of the algorithm. So we are taking the argmax, the maximum. Is there? Yes. Sorry. The argmax of the projection on the space that we have already built of all the offline solutions that we still have playing. Okay. So these are all the methods that we have been speaking about. And now we'll see how they behave. Okay, now we also need, now we pass to the online stage. So before was the offline stage. Now in the online stage, we need to define a measurement sampling method. So for the moment we take uniform sampling. We can take also grid, or you can choose an optimal sampling method that we spoke before. Like maybe once you know which is your use basis, you can try to find where to sample in order to get the best approximation guarantees. But well, not implemented, maybe for homework. So we need to evaluate. Okay, now we will go into the passive settings. So the measurements are the points where we will measure are given, and so we can do beforehand, given our reduced basis, get the evaluations for each of these reduced basis vectors in the points of measurements. which will allow us to build our matrix that we want to inverse or solve the linear system that will give us the approximation to the inverse product, to the solution of the differential equation. And so for state estimation, so here you see given measurement points, the values that are observed, and the reuse basis in particular we are using. So we need to evaluate in these measured points the different elements of the reuse basis, and then it accounts just to do a least squares, linear least squares on this pair. And with that we will get the approximate solution. Here, eventually one can put maybe a weighted least square and maybe consider different ways depending where you are putting your samples. For example, if you are sampling more in the borders where the discontinuity of the diffusion coefficient happens, maybe you need to sample more there in order to get better how the function is changing. So maybe you can add some weights, so you can modify a bit this and not be just a regular least squares. But at the moment it's just that, and it works. Okay. So here we are seeing what we are seeing. We are seeing a particular solution of our particular snapshot with the measurements that are sampled. We have in total 25 measurements. The reuse basis that we are using, it's random, so we are building a reuse basis, and here has only one element. Okay, and here we can control which is the solution we are getting. So here, because we have only one element, here the approximation will be always be a multiple of that element. So you see, even if I change the solution, we always get the same approximation. Because for linear space, it's just one dimension. You cannot do much for the moment. So even if I go like this, we will not do any much more. If we change now, we have two elements in the reuse basis. Things maybe start to change a bit. And if I move this, okay, these things will start to change, but maybe still is not enough. Well, it tries to do things. Now has a bit more of freedom to move. Maybe instead of random, we can change to PCA, for example. And try to do something. Okay, maybe it's a bit better. But still, maybe it's too small. We start to increase the number of elements. For example, there. Okay, now it starts to answer. It starts to still maybe does some strange things, but at least starts to reproduce much better our solution. And maybe we go with the greedy. 7. Also, consider we have only okay, here 50 measurements, and we can increase the number of measurements, and this can give us better approximations. But if at some point we go maybe there, we will start to see something that it's really nice. I mean, it's mostly following the actual solution and just using these point measurements. Okay. So yeah, basically this to show how the different methods can work, and yes, you need some you cannot work maybe with a too small dimension, because then you will not be able to do much, and you need some dimensionality, and the number of elements will be related basically to the to this Kolmogorov decaying rate. So if this decay rate is, for example, exponential, then you don't need too much elements. Here we saw that only with 15 we are approximating things that are, in this case, the space was 225, the original one. So with not too many bases, we are already building something that is able to approximate the.
And maybe you just said, if you can recall, how do you do the random sampling?
To create the reuse basis.
No, for the measurement.
For the measurement, just this uniform so here on these points are just uniform 0, 1, 0, 1 on the domain.
But okay.
You could do some things better. I mean, just now it's just that.
Okay.
But a bit like the question that was done before, maybe you can choose them beforehand, and you say, okay, I will choose them. So I mean, there's two situations. So you have your reduced basis already built, then you choose your measurements in places where will enhance your reduced basis to work better. Or also maybe instead of maybe you have the samples, but maybe you can change also the weights in the least squares method to consider some of them better than others to build the. Yeah, you can still play with some variants. Okay. So here are just different examples we have seen. And so finally, we want to see. Okay, here we have just done one particular thing. We want to see now the decaying rate. So we'll increase the number of elements in our basis and see how the error behaves with respect to approximating anything in the manual. So this one. Okay. So it takes a bit more because it will has to, for each n has to build the basis, approximate, etc. It shouldn't take too much. Okay, here is some preliminary data. I think this one is better. Oh, yeah. So what do we have here? Well, the blue one, don't look at it. It's the polynomial basis. So it's like instead of a high grid, we have a coarse grid. So the distribution is very not good, and it's not doing good. But then we have a comparison between PCA, greedy, and this is the random sampling the manifold. So different ways we have to build the reduced basis. And we see that in truth all of them behave pretty well in the sense that we increase the number of elements. This is logarithmic scale L2 error, and here I think it's yes, this is not L2 error. It's the worst case. And so what we see is that they decrease exponentially. Okay, so they have this guarantee that we have seen before in theory and how this algorithm should behave. And so we see it in practice also that goes down like that. And so we were looking before like 15 elements, and with 15 elements we have already more or less in 10 to the power minus 9 of error, which okay to the eye is no difference. And we go with 30 for example, and we are almost arriving to the machine precision. So pretty well for this problem in particular. But just to give us also the idea of how in practice all these things that we have been speaking about finish to enter in the game. Any question about this?
Is there any significant difference in computational time between the methods?
You mean
between greedy or just
here? I mean here the computational time is before the offline stage. Greedy it's more time consuming, then maybe PCA, and then maybe random sample. But once you are in the online stage, all of them are the same. Because once you build the basis, you forget how you build it, you just use it, and you use it the same way.
There are some differences in the behavior with the addition of some noise. Maybe some algorithm that performs better than others.
Yeah, I mean, with addition of noise, yes, that will impact, but in principle, all of them should work more or less the same.
Okay,
Once
so you just
do it.
rescale the y-axis, but
Yes, it will. Yes, it will shift. Maybe the conversion will be slower, or you have. I mean, you have some limit because you have too much noise. You cannot do too much. But in principle, I would say that all the algorithms, once you have it, they will more or less behave similarly, even with noise. Good. And okay. So okay, now yes, was a comment about the optimal sampling that because yesterday also was commented about this work, and I mean it's interesting just to give an intuition, a small intuition about it, and the fact that well maybe eventually it's to be done to implement it. But the idea is that once you have your basis built, you would like to maybe say, okay, now in the active setting, I would like to sample beforehand, know where it will be the best to sample. So the idea is to sample following some kind of distribution, some probability distribution that is linked to the basis you have built. So this function here, it's a function, it's called the inverse Christoffel function. It's just the sum of these elements, and these elements are the orthonormal basis built on the Lie space. So I will just draw something here to have an idea what does it mean. So imagine, you have you have your basis that you build. You get an orthonormal basis of that, and the thing is that each of these elements you should think of it as a function. So for example, in our case, we have a 4-domain thing. So one element of this linear space will be something particular solution, for example, like normalized and everything. So this LG will look like something like that in our problem, okay, because it's one of our elements. And what is saying this intuitively is that I would like to sample where this function, this basis function, has the most variation. Yeah. Because, for example, if you imagine here, this function goes to 0 here, just to say, so this is equal to 0 is the level side, and I sample at this point, then I will not get any meaningful information to tell us which is the coefficient for this basis function that I should put in the regression problem. So basically, the intuition about us how to sample goes to search for the places in which our orthonormal basis has the more variation. Otherwise, you will have something that is maybe ill-conditioned at the moment of doing the least squares method, or even if not, but you will not be able to differentiate much between the different basis elements you have. So the best you can do is to try to find the places in which your basis functions have the most peaks. And so that's what, I mean, this square of the basis function is telling, or the sum and normalization gives you at the end like a probability measure on your domain and tells you where you will like to sample and you get the best out of it. More or less intuition. Okay. Just this small part to tell about the limitations of these real spaces. You have seen like practical examples that work pretty well, but of course You cannot solve everything. There is always problem, limiting scenarios. So you have seen that for elliptic and parabolic problems, you have this exponential rate. And the thing is that we know that for hyperbolic PDEs, so normally when you have a transport involved, or discontinuities or shock discontinuities that are created, for example, a Vargas equation or just transport, the Kolmorov width, so the best possible thing you can do with the linear space, doesn't decay as not good at. It's a very low decay rate, so you don't hope to get good approximations with these linear spaces. So you will need something else. And so this is why, okay, some of the motivation, okay, this was a GIF originally, so well, okay, now it's a PDF, so no. But it is, okay, maybe you have to go some, we need to go some non-linear techniques. Okay, we just use everything we have of linear techniques. We need to go something linear. Okay, one hype option is the neural networks. We will see what we can do or not with them a bit. And so, yes, this is for the fourth part. So we'll speak about machine learning approaches to also these two problems, forward modeling and inverse problems. So, just a first technique that I worked a bit before, and I think it's interesting at least to just mention it and have it because it can be useful at some point. It's particularly for inverse problems. And the idea is that you will use, so the idea is that we have a system, for example, it can be an ordinal differential equation, but also can be a partial differential equation, and you have measurements. So you measure this, and you have a lot of data about it, but you don't know which is the, okay, it can happen two things. One thing is you don't know, you know which is the equation behind, and you don't know the parameters, or you don't know even there is a modeling equation behind, and you would like maybe to find one differential equation that can model the behavior of your data. In our case, we have like a temperature time series, and we knew that because these were simulations made with a super big simulator with various stops inside and velocity, pressure, taking into account about the climate and the atmosphere. But the only thing they gave us was only the temperature. And we asked ourselves, is it is possible to recover anyway some kind of modeling equation that only using the temperature you can get something. And so the idea what you will do is to build from this data. So imagine this is x, y, z, so it's like the time series. So you have the time series, and you can build a dictionary of functions created out of this data. So maybe you can just square the value of x, you can multiply them in between, and also you can maybe calculate derivatives using finite differences. And so you build this this big dictionary. So you will see it as a very big matrix. So you can see it as a very big matrix, where here you will have, for example, x, y, x times y, the finite difference is like t time, I don't know. And so because this is data, you can just put it here, the values, multiply them and put it here, put it here, put it here. And you know that on the other side you have your target, what you want to approximate. That will be, for example, the derivative of x, the second derivative. So you calculate this also with finite differences, okay? And so you want to try to find, for example, some equation. Yes, okay. It's here, but imagine you will, the true solution is something like for example, 2 times x minus t plus the time, just to set, no? So in truth, it will be basically this vector that you get with your data. We'll be multiplying twice this vector minus 1 this vector and plus 1 this vector. And the others should be 0 because they don't intervene in the equation that gave originally this data. So this data came, imagine, from this equation, and now you want to recover it because in truth you don't know. You only have access to the data. And so the idea basically is that once you build this matrix from one side and the vector, this your target vector from the other side, you will minimize the approximation you get here using some regularization, normally L1 penalty, that will enforce the coefficients associated with the vectors to go to 0 if they are not meaningful to reproduce, to try to explain this variable. And so what you get at the end, it's basically the coefficients you will get will tell you which are the coefficients that are still alive. It tells you which is the differential equation basically that may be used to model this data they do. So you're doing this inverse problem, but also maybe you're doing even more because you did not even knew at the beginning which was the differential equation, and maybe you are finding a possible modeling differential equation that may help you solve this problem. Okay, here we are just using still minimization. We didn't enter full machine learning as usually said. There's no neural network there. And so now we'll try to enter this, and we have different ways of modeling, of thinking about how machine learning can be set to solve this kind of problems. So, for example, if we want to do the forward modeling, we can set it in different ways. For example, one, it's if you give me the parameters of your equation, the position and the time, for example, I would like to know the value of the function at point, time, and these particular parameters. So this is like pointwise because you give me everything, I will give you one value. But also you can be interested in the complete solution. I give you the parameter and you give me everything, which is more similar to the thing you have been doing. If you give me the parameter, I will give you the complete snapshot. And you can phrase it in different alternatives. One also could be, okay, you don't give me x, you give me only the time, and I will give you the snapshot in space. Or you can be something iterative and say, okay, you give me the next time step, and so you can build maybe something iterative in the sense that you build the next value, then you enter this in your machine to build the next value. And the question is, what we put here in the middle? Yeah. So for the moment, we will just a black box. There is nothing there. Now we will start to uncover it and see what is inside. For the moment, it's a mystery. You will have in your mind maybe neural networks, but it can be much more than just neural networks. And so, what usually in machine learning, if we forget about PDEs, usually the setting, it's in supervised learning especially, is you give me pairs of, in this case can be like some parameter, in this case an image, a lot of them, I put them in a machine that will learn, will try to fit this map, and then I will use some others that I have not used here, it's important, to test, to see if our model, okay, did its job or not, how is it behaving. And so, at the beginning when I do nothing and we have not trained it, it has not learned anything, it will basically give nonsense, it will just noise, because you give something, it will random babbling, and at the end you get just random things. The idea is to have, which is the method, the thing you would use to make the model learn, and at the end of some process that will take a long time or whatever, give something that can basically approximate the mapping you are searching for. In our case, this is just the parameters of our PDE and this complete solution. It can, in principle. So there is the setting, the supervised setting is more or less the same. There is no difference. The difference that it changes the data, and we have to. And so this thing, for example, we can again, like we did with reduced basis, we pre-compute in an offline stage a lot of solutions with the solver that you know, and then we use this information to train our model. Once it's trained, then we can use it in an online stage and have things that in principle should have good approximation to our mapping. This is for forward modeling, but in truth for inverse problems it's basically the same. The only thing is we invert basically the order. So even if you build already your data set, you can change the order and try just to do the same job that you're doing, but now you are trying to approximate the inverse mapping. Okay. So let's just zoom a bit the zoo of machine learning. There are a lot of techniques and things, and yes, linear regression is also inside it. And you start building things from it. And we'll focus. Okay, yes, we'll focus a bit on neural networks. But in truth, what we are really interested is not just neural networks, but in truth, any differential program. So this is an example for the neural network. Neural network is just a combination of what is called layers. So we have an input that will come here with some values. In our case, can be the parameters of our differential equation, and those are like linearly mapped with the linear transformation. We add some bias to move it to rescale it, and we applied a function that should be nonlinear, because if it is linear, then everything will be linear, and we are just doing linear regression. So these functions typically have a lot of choices. You can put sigmoids, hyperbolic tangents, and there is also rectifier linear units. I mean, there are a lot of zoo also of activation functions, and depending on the problem, ones may be more relevant or not. So it can be important what you choose there. An important thing is that after this, will give you basically your forward pass, and at the end you will get a prediction that will be, in our case, our solution of the differential equation, and you will have to measure the error you are making between the output and the example, the training example we are giving to the program, to the neural network to learn. So this usually, depending on the problem, but for regression, usually it's the L2. So we just calculate the difference, the error we are getting, and summing over all the examples that we have been given. So here basically we are going to predict for each, for each parameter, the neural network will give something. At the beginning will be this, so nothing relevant. But we have a way to measure the error between this and this, and we will use this error to try to change our parameters of the neural network in order to minimize the difference between what it outputs and what it should have outputted. And to do that, everything is based on two things. So learning for us will be a combination of the chain rule and an optimization. So once we have written this problem as with an error function, then we have just to differentiate this function with respect to the parameters, the trainable parameters of our neural network. So here what we will do is an optimization over all these W and B that are inside our composite function. And usually, because these things are differential, you can go through the end and get how much each of the parameters should change in order to go down in the optimization process. What does it mean go down? It means minimizing this error. The hope idea at the end is when you go really at the end of the optimization process, you will get something that the error will be very small. Okay, this is in truth also very complicated. I mean, the algorithm is pretty decent. You always go following the gradient with respect to the parameters. And the thing is that usually these things are super non-convex, have a lot of local minima. The thing you are trying to optimize is super strange, so you don't have usually as nice guarantees that when you have linear approximation or convex approximation or optimization and these kind of things. But still, in many cases, you can do very good. Yes, you can do it. And the thing is, even sometimes you don't really want to go to the real optimum and the global minimum. Because in many situations, if you go to the global minimum, it means that your neural network has overfitted. It means that it had learned too much your training data, and it is not allowed to generalize. So when you give it new data, it doesn't know what to do, because it only knows how to do with the things you have already given. And so, in truth, it's go to a minima, but not necessarily the global minima, because the global minima is not necessarily the good spot you want to be. Okay, so all this is based on the fact that you can do what's called automatic differentiation. So just explain a bit, because also for me it was kind of strange and still a bit dark what is behind it, but just to get a small idea what is happening behind there's like TensorFlow, PyTorch, all these libraries that are made for helping do machine learning. They rely on the fact that they can differentiate the things you program. And so the thing is that when you build your operations, for example, neural network, typically is your input is just a variable. Then you will multiply by a linear transformation, a matrix. This is differential. Apply a function that is non-linear. Then you have to build this function to be differential. So for example, hyperbolic tangent and all the ones that I mentioned are differential. So you can differentiate on them. And so all these combinations makes the full pipeline differential. So you can go one way and then also you can go back doing the chain rule. Mm-hmm.
The neural network is a fully connected neural network?
Can be, cannot be. In principle, usually yes. Usually when you build a fully connected neural network, because a priori you don't know where to prune, where to cut. There is some neural networks called Bayesian neural networks that at the beginning you do it fully connected, because they are based on like a probability. So they, at the end, what you get is a probability of activation of each like path somehow, and at the end you can cut the paths that you know that are not too much used, and at the end you get a neural network that's more like more data efficient in the sense that you don't need to have the full thing. In the training, yes, so that will be computationally expensive, but then at the end you will get something that you can shrink in data manner, in a sense. But usually beforehand, when you just start, you use fully connected, because a priori one doesn't have a prior knowledge of knowing, okay, yes, I will cut here or there, I don't know. I will let the neural network to train with full thing. But also there are like many different architectures. I mean, the forward, this thing I wrote here, it's just the original basic neural network, but then you can try and see that there is a zoo of a lot of different kind of things depending on what you do and the kind of problems you want.
Another thing, I suppose that F is a nonlinearity.
Yes. Exactly.
And it can be only a differential or nonlinearity. For example, you cannot use the Hegelian or the Hegelian function.
You can use it because, okay, it's not differential in one point maybe, but it's differential everywhere else. In principle, I mean, even if you fall there, you can just say, okay, the derivative there is just the left and the right derivative. Yeah, so the thing is that you can I mean, in principle, it's not that you cannot put things that are not differentiable. The thing is that if you put something that will not differentiable in parts or whatever, you will not be able to use this to optimize. It's more like that. If you will rely on this to optimize your problem, then you need the thing you write to be differential in all the steps. So as long as you have something, even maybe yes, in that case it's 1 point, but you can still solve that situation. But if you have things that maybe are not so nice differential, then in that case you can. But yes, you need some differentiality to use this. Then if not, you can use something else. There are other kind of optimization algorithms, for example, because one other thing is that here we have these parameters, and one also can ask, for example, as you said, is fully connected or not. Also, one can ask, okay, how many layers do I put? How big these matrices are? A priori also, you don't know, or you just maybe build something, hoping that it has enough rich expressivity capabilities to be able to explain your problem. But a priori you don't know. And so there is a lot of work also in what is called hyperparameter optimization, which means, okay, I optimize, I do this for this neural network. Is it the best? I don't know. I will just create a new neural network with different shapes, architecture, and do the same process. And at the end, I will get only the one that went better between all the others with some other metric. And for doing this, because that is definitely not differential, because you are changing one architecture to the other, that's kind of not working so well in differential terms. So these optimization algorithms rely more on basically sampling, because here you are sampling neural networks basically, and try to optimize how you sample to try to converge to a neural network architecture that is the best. And so that there, for example, is also an optimization and doesn't rely on gradient descent on these things. It's more like pointwise evaluation. Some of them are based on genetic algorithms using the previous sample evaluations, where maybe you should go in the new samples. Also, there are Bayesian algorithms in which they try to guess some kind of function that tells you, okay, if you go this way, you may have more probability to find the maximum here. And so they try to create the architectures that will go that way. But in that case, it's not differential. So, in the case of differential, so now we are in the neural network, and so the thing is that every operation that you put in the neural network, or in the we call it differential programming. But that's one of the things is okay, usually everything starts with neural networks, and now it's a big family of methods and things. And the relevant thing here is that is differentiable. So the thing is that we'll have an operation. In this case, for example, is the multiplication operation, and just we know how to differentiate the multiplication operation with respect to B or A, for example. And so basically, what is done in differential programming is that every operation that you will do, you will program the operation, so you will program how to do the multiplication, but you are also interested in knowing how to do the derivative of the operation with respect to the inputs. And so and it's interesting because depending also on the programming languages, but for example in Python, you can, it's called overloading of the function. So when you define the multiplication in Python, when you multiply two objects, if these two objects have defined a multiplication, then you can do the multiplication, but there you can put whatever you want basically. So you can put the actual multiplication, but also you can put the calculation of the derivative. And so when you do the multiplication, the output behind the carpet will be the value of the multiplication more the gradient that eventually you will use. And so usually in this process of optimizing, you have two steps. One step is what's called forward pass. It's now you give me the input x, I will just multiply, go, pass through all the neural network, and then I need the backward pass. Backward pass is calculating the derivatives to do the chain rule, calculating this up till until the end to know how to actualize, to modify the weights. And so to do this backward, you need the derivatives at each step. And so basically, this is like that. You will program, or they have programmed in TensorFlow, PyTorch, etc., how to differentiate the different operations. So multiplication, summation, exponential, I don't know, any operation that is differentiable, even a for loop. I mean, you can. They have done it. So you can, when you go for the forward pass. So here the green lines are the forward pass. It means A was set to 2, B is set to 3. So we have these two values. They will be multiplied, and so you will get the value of 6. So this is the forward operation that we know. And this will be passed to the next steps. So this continues, I don't know, continues there. And then at some point it finish the forward pass. And now we will start to compute backward the gradients with respect to the operation we have now. And so at some point these gradients come back, and it enters this node, let's say, with a value of 5. 5 means that the gradients that we have accumulated from the end until here sum up to 5. And now we need to propagate back this derivative back using the known derivatives of the operation of multiplication. So the derivative of this operation with respect to A is B, because it's simply the multiplication, and the derivative of the operation with respect to B is A, because this is also the derivative. And so now we will propagate this back multiplied by the derivatives that came before. So you are accumulating all the previous derivatives more than new ones that you are getting. And the important thing is that maybe sometimes, because when one thinks, okay, this is differential programming, and one thinks, okay, it's the derivative in all the space and everything. No, this is like point value differentiation. So this thing will not tell you the derivative everywhere. It will tell you exactly where you have evaluated your function. So you put values x, you go forward, and you will get at the end the exact derivative of your function evaluated in the x of the input. Okay. So this is more or less the idea what is behind, what is happening behind when you do automatic differentiation and when you use these libraries. Okay, good. So now physics informed neural networks. Because all this introduction was because this technique, so this way of approaching the solving the forward modeling or inverse problems doesn't rely with the same. It's not the same philosophy that we explained before. Before the classical setting of supervised learning was you prepare beforehand a big data set of things that you will put to give to the neural network, usually in descent, to optimize and learn. Now the idea is that because this is okay, this you cannot do it any other way. For example, if your problem is classification of images, I mean you need images to learn what they are and what you want to classify them. But in our case, we are working with partial differential equations. We know what the equations are, and we will manage to incorporate this information at the moment of training and the moment of telling the neural network what it has to learn, without necessarily going to the expensive task of creating a big data set of particular solutions in order to get the approximation. And so the thing that we will do now is forget about creating a data set beforehand. We will work only with the differential equation. So So now, when we write the differential equation here, for example, usually we write, okay, this derivative on time with respect to v with respect to time, v with respect to x. I equate this to 0. We have here the parameter, and okay, this. Then we say, okay, we have to solve this. We have to find which is the function v that solves this, which means for each x and t, this thing should be equal to 0 for the given function. That's basically the definition of the solution of the differential equation. The thing is now, we will do is say this v will be our neural network. So our neural network will be the function that will approximate the solution of the differential equation. Which includes what we had before. We have also before that if I give time and x to the neural network, it should give the value of the function, the value of the solution. The difference is before, to learn this, we gave a lot of examples, and so we're trying to learn this through examples. Here, what we will do is to write this equation using the differential equation here, the neural network here, and relying basically on the fact that we can do automatic differentiation. We can derivate the neural network with respect to the input. So we can derivate it with respect to time and x, which are the inputs. So this basically, when you do the derivative in time of your neural network, is again chain rule until the time, until the input. And so you will get something, it's a function, that is not the neural network strictly, because in the middle you have like the neural network tangled with the gradients and whatever. It's some object that still you can work with because you know how to do all this process. And you can sum, you can do things, because it's still a function. It's a function that gives you the derivative of the neural network with respect to time. At the beginning it's just that, because now I haven't learned nothing. I'm just doing the derivative of your noisy starting point. The neural network gives nothing, gives nothing, it's random things, but this, what it gives, I can differentiate it with respect to the input. So I just differentiate it, I differentiate it also with respect to the other input, and I can write this equation using these differentiations. And so when I write this equation, then what I will, at the beginning, this will not be true, because you put random initialization, so the derivative of the time of the neural network plus this thing will not be 0, will be something, I don't know. But what we want is to get 0. So we want to force the neural network to learn the structure of the differential equation, so when then we just sample time and x, it will give you the actual value of the differential equation, the solution. And so this means that this thing, we can put it inside the cost function, so the error function that we want to minimize. And instead of having examples, now it's just writing this with the automatic differentiation tool. And the thing is that still we cannot like just write it like that, xt in general, because as we said, like the automatic differentiation works point by point. So we need to give points still, so it's still somehow similar to the examples that we had before, but now we don't need to compute the examples. We just need to sample the domain in different points. So we choose xi, ti at some points. We do the forward and the backward, and we will get the derivative with respect to time, with respect to x of this, and what we want is this thing to go to 0. At the beginning will not, but now that we wrote this, now yes, we can apply again the chain rule and everything, but now it's with respect to the parameters of the neural network. Yeah.
So you just random sample the points on the square, or you can use a grid to choose xi and ti.
Yeah, you can do many things. You can do random sampling. You can choose the grid. I think in the original paper, and some people use it's called
Cube sampling.
Latin.
Yeah.
Latin square.
Latin cube sampling.
It's basically, correct me if I'm wrong, but basically it's like you kind of do a grid, but then you sample randomly, but trying to like to try to in each column and row of your grid, imaginary grid, to have one sample point, which forces somehow to have one point more or less everywhere, still being random. But yes, like a combination of the grid with the random sample, and this gives, in general, good results. Because yes, and just a comment. Now I come back, but because I have a comment on this. Yeah, that here are some examples we have been working on. It's just the transport equation, the position, the time. So you have like a characteristic function that will propagate because you have just a transport, it will move. And we want to learn it with physics from neural networks. So you will sample the domain and well, it will learn. But if you sample far away from the initial condition, for example, there is no way to like connect the initial condition to the actual solution it's trying to learn. And one solution of this is just 0 and 0. If you put everything 0, it will be a solution. So basically, it learns everything 0 except just in the border because it has to be good with the boundary condition, but basically good with the boundary and then 0. So the sampling is relevant.
But during training, you change the points or just fix them at the beginning?
Well, there you can change, you can fix it. I think in the original they fix it, but then you can play with changing it.
So maybe you have a question to the answer to my question. What if I want to ensure hard constraints on boundary condition? Because basically you take like the loss function, which is composed by these two parts, okay?
Yeah.
But then, I mean, if I want the boundary that I know to be exactly the one that I know, how can I do this in the...
I mean, in some situations, for example, what you can do, as I said, I mean, you are not constrained to use neural networks as the original definition. You can add some tricks.
Yeah.
And so one trick, for example, could be if you multiply the output at the end of your differential equation. Here, at the end, instead of putting all this, you add, for example, polynomial x multiplied by 1 minus x. This is basically a parabola that forces the boundaries to be 0. Okay? Then the neural network inside can do whatever. So in truth, you will not get a parabola at the end. What you get is a parabola with the things of the neural network. In the middle, will do whatever, but you enforce 0 in the boundary. And then, well, if it is not 0 the boundary, maybe you can add something, I don't know. But in principle, if it's 0, maybe you can play with that.
But still, this is for one-dimensional case. I mean, just, okay, then you generalize to...
Yeah, I mean, with more dimensions, if it is square, you can still multiply x. If it starts to be a domain a bit more strange, yes, maybe you can start to have problems. I already have to do something else probably. And yeah, probably it's not so clear.
If I have the sampling point inside the domain, but I also some example of solution, can I do something that is between the pins and normal neural network?
Yeah, exactly. You can do that. Because here I was telling how to do the forward modeling, for example. In this case was, I don't know now, I mean, only know the differential equation, I won't just approximate. It's just another method to solving the differential equation, basically. You can think about it like that. And the thing is that here in choosing the loss function, you can add as many terms as you want. So here we said about the differential equation, and there are the boundary conditions. You want to enforce the boundary condition, you sample the boundary, and you put the boundary conditions. But also, if you have information about what is inside, you can put it as the problems we saw before. I mean, the same thing here, with the same idea. If you have information, you can add it, because in truth, it's just adding one more thing in the loss function. But also, you will complement this with the information of the differential equation. So this is basically, that's why physics informed, because you are putting the physics you know about it in the game. Before, you were just playing the same game of doing examples. Here you can combine both also. And you can do that also to do the inverse problem. Because if you have, you know the differential equation, you don't know the parameter, you know some values, then you can go back, and now this thing will be a parameter of your neural network. I mean, the differential machine will have Y as a parameter that you will use to learn.
But there is a way to balance these two kind of terms inside a loss. Because at this point I have a loss related to, okay, my solution need to solve the differential equation, nice, and then I have the other term that tells me, okay, I have some examples, so my solution should minimize my example. But maybe the loss assume value completely different in terms of order.
Order of, yeah.
And how can I balance these two terms?
In principle, there, I mean, a priori, no answer, because probably time is like problem dependent also, depending also how much measurements you have and everything. One way maybe could be, depending which, I mean, if you want to extrapolate of all the domains, so it's like forward modeling of the information, extra information. One thing you can do, I mean, you can also do this like hyperparameter optimization somehow, like say, okay, I add a parameter here there is, everything weights the same, but here we put a parameter, and this parameter you will like to maybe not learn because it's an hyperparameter, the answer you will get will depend on it, but you can, for example, if you have, I don't know, 1,000 points measurements, you get 700 to do the training and 300 to do the validation of your parameter. And so you vary the parameter, you add train, and if you get good things, then you work. But yes, you rely on playing a bit around. A priori, I don't know, I mean, not on my knowledge, it's not a way of directly answering that. It's a question also how you should weight these two things. Also, even this inside, because here also each of the sum weight the same, but I don't know, maybe for your equation it's more relevant to sample here and not here, near the border you already know, so maybe you would like want to weight more here, I don't know. And also maybe while training, also you can change the places, but also maybe you would like to change the way you are sampling. For example, at the beginning you want to consider around the initial condition, and once you learn this, then start to add points there to propagate it, to not have the problem I showed before. Then it's like branching of options.
Roughly 15 minutes.
15? Okay. Oh, fast. When we are finishing. Okay, yes, that was just a question. You can add also information about the thing of the system, and if you want to learn the parameters of the inverse problem, well, yes, definitely you need information of evaluations, but you can combine them always with the equation you have. Well, these were just some examples, because the thing is that we know that some equation, for example, this equation, when this epsilon goes to 0, the transport dominates, so this is the derivative mix, derivative in mix twice. So these things becomes very sharp, and traditional methods fail. I mean, they have not good warranties in those scenarios. And we wanted to see if maybe this kind of physics informed networks or other things could solve this issue. Not for the moment. So yes, we'll start getting. And well, yes, these advantages, you use automatic differentiation, and not this for specific data sets. This is that efficient because you don't need to have really to build offline anything. You just build it. The only thing is that for new parameters, you need to train the neural network again, because once you train the neural network, basically gives you the answer for this particular solution. So if you are in an online setting, this optimization can take time depending on the complexity of your problem. And so it can be a drawback, because maybe if it takes 2 hours to optimize, then at the end we didn't win very much. With the other technique, with the linear space, it was much faster. But well, then you can play maybe with the size of the linear network to stop it before, and you still get something that is not super accurate, but still well. Okay, but you have to play with it. Okay, yes, something relevant we have discussed. And it's known that if you go to higher dimensions and you start to add more dimensions, they start to not work as well. Because also, I mean, maybe intuitively you have to sample inside, and if you have many dimensions, okay, you start to need to sample too much, and maybe you don't really converge to nothing good. Okay, just I think we can finish here. We can finish here. This, I mean, this is work we have been doing on physics in neural networks and comparing it for this problem. And we were asking ourselves, because here the loss function we are using is the L2, the residuals of the equation. But maybe it's not the best. Maybe you can do something else. Maybe if you think of the weak formulation, maybe you can try to write the physics in neural networks in the weak formulation and try to, maybe it's better in that case.
Yeah, but in that case, there is no problem of the integration step. I mean, if you pass to the, because I also thought about that for the BEM methods, but it was like a mess then with the integrals.
Yeah, true. There you need to add the integrals because you need to do the weak formulation, and so you need to approximate the integrals with Monte Carlo, with or some other technique, and yes, you start to have also some errors. For the moment, in truth, it didn't work as well. Still, this was better than using the weak formulation, at least for this problem, because I mean we tried this problem in particular because we are interested to see if there it will better, but not for this case. Yes, well, so this you can play around. It has some also variations. If you change the epsilon of the equation and different things, you can see how the behavior of the different physical neural networks approaches and the finite element method work. I think this is all. Maybe there's a conclusion. Yeah, okay, yes, that's conclusion. But the conclusion is more or less what we have seen along all these things. At the beginning, we worked about the linear spaces in theory in practice. We saw more or less what we can do in practice. We saw it in the Jupyter notebooks. And then we saw some machine learning, framework, how you can think about doing things with machine learning to solve PDEs, and particular the physics informed neural networks. That it's one way. There are a lot of other ways of also introducing information of physics. This is just one. For me, it seems interesting. You can go around seeing many other things.